right, I guess we'll go ahead and get started. As always, if you have any questions, go ahead and ask them. It looks like we might not have anybody today, but I'm going to press on. We are in chapter 22, which is discussing Gauss's law and applying Gauss's law, and I'm going to show you several examples of that, and this should finish off chapter 22 today. I doubt I'll go into chapter 23, but we should definitely finish chapter 22 today. So let us begin with our first example. Of course, remember last time we did do an example, and I also explained something to you, specifically Gauss's law, which says the closed integral of E, the electric field, dotted with dA, a differential area element of the closed surface, is equal to the total charge enclosed divided by epsilon naught. That's Gauss's law. Now, Gauss's law is always true, but it turns out you with a little bit of trickery and I don't know, trickiness, we can actually try to extract the electric field magnitude out of that integral equation under certain symmetries. So, for instance, if we can create a Gaussian surface uh, on which the electric field is either exactly perpendicular to the surface and therefore constant on the surface, or any other parts of the surface that don't have the electric field constant on it are perpendicular to it, those parts will actually have electric fields that are either zero or parallel to the surface. So as long as we can find out some symmetry like that, then we can make a hypothesis regarding our Gaussian surface. We can make a hypothesis regarding the form of our electric field, and then we can go about using Gauss's law to work out the left-hand side, which always, when we're doing it this way, becomes electric field strength times some kind of area. Sometimes it'll be a couple terms. Sometimes it'll have a number in front or something like that. But it's basically going to be maybe some terms that are zero plus something times an electric field. That's what the left-hand side is supposed to be. It turns out that that's the case when you either use spherical symmetry or if you use an infinite plane and the symmetries thereof, or if you use an infinite cylinder, like we did in the very first problem of the very first integration problem that we did in chapter 21. And I think it was the second problem that we worked with Gauss's law. So, that's the big rule behind Gauss's law is in order to use it in this particular way, again, because it is Gauss's law, but in order to use it in such a way that you can determine the magnitude of the electric field, you have to have spherical symmetry or infinite planar symmetry or infinite cylindrical symmetry, so an infinitely long cylinder or wire or something like that. I will remind you that in the physics world, infinite means infinite, but it also means very much less than infinite. So, for instance, if you're 5 centimeters away from a wire and you want to calculate the electric field uh, at that 5 centimeter mark away from that wire. If the wire is long and straight, we can do it as long as, let's say, the ends of it are at least 50 centimeters away on each side from the point, the position that we wish to know the electric field. So basically the rule is if it's about 10 times farther away than you are from it, then it can be considered infinite. I personally prefer a factor of 100, but 10 is really sort of the mathematical minimum. So that's what we often do in physics. We refer to things as infinitely large when they're not necessarily infinitely large, but rather a factor of 10 larger than any distances we're dealing with. So we now have another student came in. Thanks for coming in, Jen. I'm going to go ahead and start. I've already talked a little bit. You can see that at the beginning of the video when we actually, one thing I do need to ask you, it did pop your name up on the screen. Is that something that is going to be a problem for being on the video because it showed both your first and last name? And I'll edit this part out too, so don't worry about that. Let me. She might be typing it in chat. She is not typing in chat. You there, Jen? Is my audio working? Yeah, my audio is working. All right, well, we'll go ahead and get started. Jen might have stepped away for a second, but I'm going to start by sharing my screen. So let me share my iPad screen with you, and you can look at example one with me. Okay. So, hey Jen, are you there yet? Can you hear me?
Yeah, sorry, Zoom was acting up. It's had
Yeah, it was
trouble.
going real slow. No problem. I was telling you, I had already started when you finally came in, and therefore it showed your name, your full name on the screen for a couple seconds. Is that going to be okay, or do I need to go back and edit that part out since it showed your first and last name on the screen? You don't care? That's cool. All right, thanks, Jen. Well, all I did at the beginning of the video was just remind everybody what kind of symmetries need to be in place for us to use Gauss's law in that weird way. And now I'm going to go about using Gauss's law in that weird way. Okay, so example one, a charge Q, capital Q, is on a solid spherical conductor of radius r. Calculate the electric field produced by the charge distribution for A, R less than big R, in other words, inside the sphere, B, R greater than big R, in other words, outside the sphere, and C, discuss R equal to R. So something's going to happen at R equal R that I like, and I want to express it to people because it is a big fundamental concept. So we're going to start off with solution here. What I want to remind you of, which you may or may not even know, much less remember, uh, in chapter 21, I don't know that I explicitly reminded everybody, but I know it's in the reading. But in chapter 21, we learned that when you distribute a charge on a conductor, basically the conductor is going to because it's a conductor, it has the ability to allow free charges to just roam about the conducting material. And because of that, it turns out that all the individual charges that you release on a conductor will repel each other so much that they ultimately end up to be distributed more or less uniformly over the outside surface, and that ultimately causes what we'll see now, that at least in a static situation, uh, the electric field inside of a conductor is always zero. So that's a big point that we sort of learned from the reading in chapter 21. And now that we know Gauss's law, we can sort of show it just by realizing that all the charge in electrostatics, all the charge that you put on a conductor will reside on its outside surface. Okay, so we are going to make use of that. We're also going to make use of Gauss's law, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And that's pretty much all we need right now. The rest is just, building on experiences and things that you've seen so that we can solve the actual problem. So I'm going to draw a coordinate system just because it's nice to have a picture to use when you're thinking about physical problems, because sometimes that gives you insight into it that you might not otherwise get if you hadn't had a figure. So here's my x-axis, here's my y-axis, and here's my z-axis. And I'm going to attempt to draw a sphere, and I shall draw the sphere of radius 3 squares. So here, 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 and technically it should probably hit somewhere right about here on this one. So I'm now going to put it on the drawing command where it sort of makes my crappy drawings into a good one. Hopefully it works. Yes, it worked well enough anyways. So now that is a sphere of radius big R. And the total charge, by the way, is Q. And I can draw this just to remind everybody that it's not a circle. It's a sphere, and I can draw this the same way. So remind everybody that it is a sphere. And what I'm going to do is I'm going to go ahead and try to calculate for part A. We're going to try to calculate, oops, forgot it should be working in purple. We're going to calculate the electric field for R less than big R, and reminding everybody that this radius and here is big R. Okay. So what we do know is that the total charge on this conducting sphere is plus Q, and specifically that it all resides out here on the outside surface of the sphere. None will be inside, basically. So we just sort of have it uniformly distributed around the outside. So it's still a spherical distribution. And in that sense, just like we learned in the gravity chapter on chapter 6, Newton worked out that basically the gravitational field only depended on uh, basically the distance away and was highly symmetric and that sort of thing for any spherical mass distribution. So the same thing occurs with this Gauss's law, electric field distribution, that when you have a spherical distribution of charge, it acts just like a point charge at the center of the sphere. In the case here, though, we have a conductor, and as we learned, all the charges that you put on a conductor are going to jump out to the outside edges, and therefore there will be no electric field, or excuse me, there will be no charges inside. So let's start off with E for R less than A, and technically, or excuse me, for R less than big R, and that is technically a vector, so I want to write that there. Now, in order to apply Gauss's law, you always have to have a Gaussian surface because the left-hand side, that closed integral E dot dA, remember the circle on it just means, hey, I'm doing a surface integral and it has to and can only be over a closed surface for Gauss's law to work. So it's got to be a surface that has a clear inside and a clear outside, and you can't get from one to the other without crossing a surface. In this case, we're not really sure what the electric field inside would be. We sort of got some hints of it in chapter 21, but we do know all the charges would be distributed out on the outside edges. So I'm going to assume what I learned in Newton's laws for gravity is still applicable here for the electric field with regards to the Coulomb force and therefore Gauss's law. So I'm going to assume that this is going to behave as if it has an electric field, just like a point charge at the origin. So if we had a point charge at the origin, we know Gauss's law says that E is equal to Q over 4 pi epsilon naught R squared. Therefore, we know for a constant radius, the electric field would be a constant. And therefore, anything of a constant radius has to be basically a sphere. So I'm going to use a Gaussian surface for R less than big R, and that's what we're going to integrate over. So now I'm going to take green and draw my Gaussian surface, and I'm going to do this at 2 squares. And again, I'm going to try to use the tool that the note-taking program has to draw a good surface. So here's my sphere, which when you're trying to actually just hit dots, it's not that easy to draw a good one, but luckily it did seem to fill it up like we wanted it to. Oh, I did not want to make it bigger. I just wanted to move it to the right ever so slightly. Uh, that wasn't necessarily what I wanted either, but I think I might have to leave it. Let's see. Okay, now it's good. All right, so there's our Gaussian surface. This Gaussian surface, of course, has a radius little r. And what we got to do is work out the left-hand side. So I'm going to say hypothesis. Now that makes me mad. All that pretty writing and it just pretended like I didn't write anything and erased it all because it tried to turn it into a drawing. So hypothesis. So there's our hypothesis. And what we're saying is I'm trying to hypothesize the magnitude, direction, what the magnitude depends on, all that sort of stuff about the electric field for the region I'm talking about. And I would say, based on the idea that I was just telling you, that we learned from the gravity chapter, that when you have a spherical distribution of mass, the the gravitational field points radially outward and shows all the hallmarks of a spherical distribution. So I'm going to assume that E, the electric field, is something that depends only on the distance r, which is the distance from the origin, and it points radially outward. So I'm going to use the r hat vector, which again, in this case, I'm talking about the r hat vector as just a vector that points always from the origin in the outward direction. So if you go to any point in space, any x comma y comma z point in space, and you drew a line from the origin to that point in space, if you continued that line one more unit past that point in space and you put a vector head on it, then that little last unit long section would be the r hat vector I'm talking about. So that's the r I'm using. In fact, you could say the r hat vector that we're using, which is r spherical. So I'll put SP. That is actually going to be cosine phi, cosine theta, I hat plus cosine phi sine theta. Actually, I don't have enough room to do that. Let's do this real quick. Okay, I'm trying to move it over here just a little bit. Okay, so we're doing that. So the second term is cosine theta, cosine phi sine theta, and that'll have a j hat on it. And then this one does actually have a k hat term, and that one's just going to be sine phi k hat. Okay, so that's what that r spherical coordinate is technically. This is the r we're using. And I think if you played around with that a little bit, even with like Desmos or whatever, you could see what I'm talking about. The main thing is I just need you to know it exists. I don't need you to be able to compute all that stuff. I just need you to know that the vector exists and that there's another one that exists that's just like this, except it doesn't have a k hat term at all, and therefore the cosine phi and the sine phi just become one in that case. So that's our hypothesis. E is equal to E of r hat. And now I'm going to write out the left-hand side. So notice how I'm doing this. You could, in principle, like work the left-hand side simultaneously that you work the right-hand side. But I find students get a little confused and forget what they're doing in the middle of it. So I recommend you write LHS, which means left-hand side, then you work out the left-hand side, and then you write RHS, which means right-hand side, work out the right-hand side, then you write LHS equals RHS, set them equal, and then solve for the E magnitude that you hypothesized. So the E magnitude, for instance, in this case that I hypothesized was E that I think only depends on R. You might actually discover that it depends on something other than R, but just, take a guess and see if it does, and we'll see what works out. So the left-hand side is the closed integral of E dot dA over the Gaussian surface, which is the green sphere. And notice it is a closed surface, so Gauss's law does apply. So everywhere on the surface of this green sphere, the electric field is going to be E of R times r hat. And what we're going to do is we'll discover that there's a little differential area element that I'm drawing right now. And that differential area element has to have that vector whose magnitude is equal to the area of the little rectangle, and the direction of that vector has to be perpendicular to the surface, and therefore it is again an r hat direction because is clearly, if it comes from the center of the sphere to the surface, then it's going to be a radial line, and therefore it points in the r hat direction. So I'm going to call that dA is the magnitude. Actually, I shouldn't be writing that in green. dA is going to be the magnitude, so I have a dot product dA. And in spherical coordinates, there's a very specific dA I'm referring to, but you really don't need to know it at all. I just need you to know sort of it exists and that in this case it's going to have a r hat as its direction. Now, because we're doing this on the Gaussian surface, this is again what I call this is what we call a surface integral. And whenever you do a surface integral, basically what you're supposed to do is take all parts of the integral and evaluate them on the surface that you're talking about. So in this case, our surface is a spherical surface of radius little r, and you can see my E of R has been evaluated at little r, so it's actually on the surface. And my dA is actually drawn on the surface of the sphere as well. And in order for it to be perpendicular, it's got to be a radial line because it's a sphere that's centered on the center. If you follow that radial line back, it'll run right into to the coordinate origin, and therefore you know it's the r hat that we were just talking about. So that's what we've done here. Now, since that e of r is in fact a constant, I can pull it right out in front, and now I just have the integral. And by the way, the dot product technically is what we call a linear operator. So I can take out, a constant between the dot product and the vector and just pull that out in front. So that's what I'm going to do. I'm going to stick the I'm going to stick the dA right here by the integral, and then I'm just going to leave the r hat dot r hat after it. So that's what I mean. My ability to pull that E of R and that dA through the dot product, or specifically more the dA, that allowed me to actually get the integral in this form. And of course, remember, dot products mean the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Since these are unit vectors, that means each of them have a 1 unit length. So I do 1 times 1, and then they're parallel, so it's times the cosine of 0 degrees. And of course, cosine of 0 is 1, so the whole thing is 1, and we're basically just left with E of R times the integral of dA over the surface of a sphere. That means, guess what? We just need the area for the surface of a sphere, which happens to be, and I'm sure you'll have this memorized by the time you get tested on this. It's just going to be 4 pi r squared. So now I have E of R times 4 pi r squared. This is also what I reminded everybody at the beginning of the video before you got here, Jen. The left-hand side is always supposed to turn out to be some electric field magnitude times some area. There might be other terms that are 0. It might be 2 times the electric field times the area, but the main thing is you're always going to get an electric field times an area if you're trying to use Gauss's law in integral form to solve for the electric field. Okay, which is what we're doing. So now I've got the left-hand side worked out. The right-hand side, a lot of times, or most of the time, is quote unquote the potentially hard spot. But a lot of times it's really easy. So the right-hand side is Q enclosed. So I got to take that Gaussian surface again, the green one, and think of all the charges that are enclosed inside of it. Do you know how much charge would be enclosed inside of that conducting sphere, Jen? So what we learned in chapter 21, again, and I tried to remind you guys about, was that when you place charge on a conductor, it's all going to go out to the outside edges. So there should be absolutely zero charge on the inside. So I'll write that as 0 over epsilon naught. Then I'll say left hand side equals right hand side. And that gives me E of R times 4 pi r squared equals 0, and that means that E, which is supposed to be hypothesized E of R times R hat, turns out to actually be the 0 vector. So E is equal to 0 for R, oops, I almost read a cursive for R less than big R. Now, if I chose to do that Gaussian surface all the way up to the inside edge of the surface, it would still be the same result because it's only on the outside surface that the charge resides. So for everywhere where R is less than big R, the electric field inside is going to be 0. And that's a big conclusion that in electrostatics, the electric field within a charger, within a conductor is always zero. Electrostatics meaning you're not setting up, for instance, a battery that could force electrons to run from one side to the other side, something like that. That would be a non-electrostatic situation. So what we're imagining is any kind of charges you just threw on a conductor and you just let them work themselves out to whatever way they feel comfortable. When that's all said and done, then you're going to find the electric field inside zero. If the electric field inside was not zero, that would mean the charges would be moving. And again, that's sort of the non-definition of an electrostatic situation. So you're contradicting yourself when you do that. But now that we have part A done, we can go on to part B, which is for R greater than big R. So in this case, we do exactly the same Gaussian surface, only now R would be bigger than little r, or excuse me, bigger than big R. So we could, for instance, say it's going to hit here, here. We had line 3 here, so I'm going to say right about there and right about there. And now I'm going to attempt to draw the second Gaussian surface. Whoa, I did it perfectly. So this is Gaussian. Whoa. So this is Gaussian 2 R greater than big R. Okay, so this time we could draw the radius right here and say that's R. Okay, so again, we're just going to start with the left-hand side. My hypothesis is still R. You could say it is again E is equal to some E that I suspect is probably only going to depend on R. And it points in the radial direction R hat again. So now I can say left-hand side, and the left-hand side gives me the closed integral of E dot dA, and the dA vector is going to be just like it was before, so I'm going to write this as the integral of E of R hat. Then I'm going to dot that with dA, the magnitude of the differential area element, which looks like a little tire patch, just like the last one did. And it's going to have an R hat after it, just like that. Again, I'm going to use the linearity of the dot product. That allows me to write this as, for instance, E of R dA times, oh, that A turned out bad. Not that bad, but my OCD won't let me do anything different. So dA times R hat dot R hat. Again, this is just going to be 1 times the cosine of 0 degrees, and that, of course, is just equal to 1 again. And since we're integrating on a sphere of radius little r, then E of little r is a constant and can be drawn out in front. And then we just have the integral of dA over a sphere. Okay, and dA is an area, not a volume, so you got to think surface area. And lo and behold, when we do that, we get E of R times 4 pi R squared. So notice the left-hand side gave me exactly the same result as I got in part A. That's what I need you guys to see, is that the left-hand side is the easy part, and if it's not easy, you did something horribly wrong if you're trying to use Gauss's law this way. Okay, it's always just going to be an area times electric field. So we've got that. Now I'm going to do right-hand side. So with the right-hand side, that is Q enclosed over epsilon naught. Now, we did say that the charge is capital Q, and that's all completely enclosed now because we've got the entire sphere, including its surface, inside the Gaussian sphere. Therefore, the total charge enclosed is Q, and the right-hand side is therefore Q over epsilon naught. Now I'm going to say left-hand side equals right-hand side. And with that, I get E of R times 4 pi R squared is equal to Q over epsilon naught. And that gives me that E of R is equal to Q over 4 pi epsilon naught R squared. So notice the R squared, the 4, the pi, all of those just came over from the left-hand side. The E0, the epsilon 0 was already there, but lo and behold, we got Gauss's law, or this is literally Coulomb's law from Gauss's law. So using our hypothesis, that means the electric field is equal to, I'll make it a piecewise function like this. I'll say 0 for R less than big R, and Q over 4 pi epsilon naught R squared R hat for R greater than big R. Okay. Now, that's the actual formula that we were able to derive for the electric field. And we're asked in part C to talk about what happens when R is equal to big R. You can see that E of R, let me write it in purple, sorry. We can see E inside is basically just going to be 0, and E immediately outside is just going to be Q over 4 pi epsilon naught R squared. So if we do E outside minus E inside, we end up getting, notice Q divided by 4 pi R squared is the charge per unit surface area. Does that make sense? Yeah, you're shaking your head. Yes, so that's cool. So we could actually call this sigma over epsilon naught. And that is really the fundamental idea that we just discovered, that electric fields, the components of the electric fields that are perpendicular to a surface, they're either going to be continuous or they're going to be discontinuous, and they're only discontinuous when there's a surface charge sigma. And if there is a surface charge sigma, the discontinuity will be sigma over epsilon naught. So that's another really big result. It again just says the component of the electric field perpendicular to a surface is continuous unless there's a surface charge. And if there is a surface charge density, it's going to be discontinuous, and it'll be discontinuous by an amount sigma over epsilon naught. If you were to plot this, which obviously we could do very easily, we'd plot the electric field versus R. The magnitude is really all that we care about. But what we'd say is this distance right here is little r, and the electric field would of course be 0 right up till we get to R, and then it's going to happen to be Q over 4 pi epsilon naught R squared at the interface. And I tried to draw that as a big R after the fact. Let me fix that a little bit bigger. So 4 pi epsilon naught R squared is what the magnitude is there. And then you see that the electric field falls off like 1 over R squared. So that's what the electric field everywhere in space looks like for a solid conducting sphere of radius big R and charge big Q. Any questions on that one? All right. So example 2, this is another one, but this time we're using a non-conducting sphere. So consider a non-conducting solid sphere of radius r and total charge big Q distributed uniformly throughout the sphere. Find the electric field for A, R less than R, B, R greater than R, and C, discuss R equals R. Okay, so solution. We're going to make use of Gauss's law again, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. They told us it's a non-conducting sphere and that the charge is distributed uniformly. Uniformly distributed means either lambda, which we've learned about before, sigma, which we definitely learned a little bit more in the last problem about, and our rho, which is what we're getting ready to use now, has to be a constant. So I can say rho, which equals dq over dv, is equal to a constant. Okay, that's nice. And the reason I wrote it that way is so that we can actually use it to make up a mathematical formula that allows us to avoid doing more calculus. Okay, so that'll come in handy as well. I'm going to go ahead and draw uh, my coordinate system again. So this time, let's try to draw it straight. I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, like that. And there you go, looks a little straighter. So this will be my x-axis coming out of the page. This will be my y-axis in the page, but going to the right. And this will be my z-axis. This time I'm going to draw the sphere. Let's say, I think I will draw it 3 squares in radius again. So I'm going to attempt to go from 3 squares to 3 squares to 3 squares so that the program will automatically draw me a nice sphere. So that almost worked perfectly, but well enough anyways. I just stop moving it after I touch it. Ah. Okay. So there's our actual surface this time. I chose to do green, not sure why, but I did. Okay. So there's the actual sphere. I'm going to go ahead and make it look like a sphere by drawing this shape on it. Oops. I'm actually going to erase that shape because the automatic drawer made it worse. And then I'm going to do the same thing here because again, the automatic drawer will make it worse. So that's what the surface we're talking about, or that's the object we're talking about, and its radius is big R. Okay, now I'm going to draw a Gaussian surface, and we're going to start off with A, which is R less than R. So I'm going to draw a circle of radius 2 squares, and hopefully it'll come out nice and neat. Not perfect, but good enough. Okay, so that looks okay, I guess. That is going to be my Gaussian surface for R less than big R. And that means that radius right there is little r. Okay? Again, we'll still have that nice little tire patch from Looney Tunes type cartoons. That's going to be the shape of the differential area element. So dA is going to be dA r hat. And then we're going to make a hypothesis, and that hypothesis is, so this is part A, hypothesis E, the electric field, because of the spherical symmetry and the fact that the charge is distributed spherically symmetric throughout or uniformly throughout, we expect it's going to act just like a spherical charge distribution. So it's going to have a magnitude that should probably only depend on how far you are away from the origin. And it's going to point radially outward. So we're going to use the r hat again from spherical coordinates. So I'm going to use that. Now I'm going to say left-hand side. And the left-hand side is the closed integral of E dot dA. And that becomes the integral E of R hat, dotted with dA R hat. And this is over the Gaussian sphere. Every now and then, I just like to remind everybody exactly what we're integrating over, so that you can keep in mind that y, for instance, the E of R can come out because E of R means the radius has been evaluated at R, which is the same radius of the sphere, therefore it's a constant. Okay, so since the E of R is evaluated on the surface of the sphere, the E of R is a constant I can pull out in front. And since the dot product is a linear operator, then I can pull the dA out in front, and then I'm just left with r hat dot r hat, which we've now exhaustively shown to be equal to 1. So again, in this case, I just get E of R times the integral of dA, and the integral of dA is the area, the surface area of the thing we were integrating. So it's the surface area of the sphere, and the Gaussian sphere has a radius r, so its surface area is 4 pi r squared. So again, you see we got an E times an area. Like I said, the left-hand side is always supposed to be an E times an area. Now I'm going to do the right-hand side, and this one's a little bit more confusing or possibly scary, and there's a lot of ways you can do it, but Q enclosed over epsilon naught is the right-hand side, and technically you could write this as 1 over epsilon naught times the integral of rho dv, and that means you'd have to do a little calculus, right? But you don't necessarily have to do it that way. You can always do it that way, but you don't have to. What you can also realize is rho equals a constant. And remember, rho is dq over dv. If we actually chose to sort of integrate that or think about it, that would mean it's literally the total charge divided by the total volume. So we could say Q, which is the total charge of the whole sphere, not the Gaussian sphere. I'm talking about the non-conducting sphere. The total charge of the non-conducting sphere is Q, and the total volume of the non-conducting sphere is 4/3 pi r cubed. So that's part of the reason why I've been telling you guys lambda you need to think of as either mass divided by length, or now you need to think of it as charge divided by length. You need to think of surface area or sigma as charge divided by surface area, and you need to think of rho as charge divided by volume. Now, we only have a small fraction of the total sphere inside that Gaussian surface. In fact, inside we have a total amount of charge Q enclosed that we want to know, but the volume is 4/3 pi little r cubed. That's the key to us avoiding doing integrals. So that 4/3 and that 4/3 is going to cancel out. That pi and that pi is going to cancel out. And what you can find is Q enclosed is just going to equal r over r, actually I'll put the exponents on the individual parts, times the total q. Okay, so I didn't actually have to do that integral. I was able to get it just this way. So now what I can do is write equals q over epsilon naught times r to the third over big R to the third, and that would be the right-hand side. Does that make sense? That q over e epsilon 0 times r cubed over r cubed. Now I'm going to set left-hand side equal to right-hand side. And when I do that, I get e of r times 4 pi r squared is equal to, oops, I forgot the left epsilon naught. Let me correct that real quick. Oh, no, I had it on the other one. That's right. Okay. So, yeah, I'm good on that. So this is going to be q over epsilon naught r cubed over r cubed. Now we can see something really cool. This r cubed is going to cancel out, leaving a 1 with this r squared. So there's a r squared on the left, and there's a r squared times r on the right. So the r squareds will cancel out, and you're just left with r on the right. And now we get that the electric field magnitude E of r is equal to q over 4 pi epsilon naught r cubed times r, like that. And we can finally say that using our hypothesis, E is equal to Q over 4 pi epsilon naught R cubed times R hat, like that. And that is for R less than big R. Any questions on that? So it turns out it's actually linear. In fact, it's directly proportional to R, so it's even more specific than linear. So as you get further and further out, the electric field gets stronger and stronger. So if you're at 1 centimeter from the center and you got a strength of 100, if you go to 2 centimeters, you're going to have a strength of 200. If you go to 3 centimeters, you're going to have a strength of 300 newtons per coulomb, or newtons per coulomb as well. So now I can do part B. You sure you have no questions on this? You good, Jen? Okay. All right, so part B, this is for R greater than big R. I'm going to draw another Gaussian surface. This time I'm going to draw it here. Oopsie. I'm going to draw it here. That looks about just under half, just under half, just under half, just under half. So now I'm going to attempt to draw a sphere. Turned out perfect. This time I'll draw the radius right here, but this is our Gaussian surface for part B. Okay, you're still going to have sort of the same little dA that we drew before. You can just imagine that one as if it's now drawn on the outer sphere as opposed to the inner sphere. But we also need to make our hypothesis, which is going to be the same thing. So hypothesis E is equal to some E of R hat again, just by the spherical symmetry of it. Now we can say left-hand side. Left-hand side is the closed integral of E dot dA, which equals E of R hat dotted with dA, R hat. And I think you all now realize that this is just E of R times 4 pi r squared. Now notice we're doing it to the Gaussian surface again, so that's why I use the radius little r, not the radius big R. Uh, that's a key thing, and that's one of the mistakes students often make is they don't know which r's to use. So just remember, you're always integrating over the Gaussian surface. So, and we hardly ever draw the Gaussian surface at the exact same radius as the actual surface. Okay, but we do on occasion when we're trying to figure out stuff, but it's not when we're trying to compute electric field strengths. All right, now we have the left hand side. Now we do the right hand side, and this time the right hand side is going to be super easy because it's the Gaussian surface encloses the whole sphere, so we already know what Q enclosed is. So the right-hand side is Q enclosed over epsilon naught, but the Gaussian surface is bigger than the green non-conducting sphere, so the total charge Q is actually the charge enclosed. So we just get Q over epsilon naught. Now I can say left-hand side equals right-hand side. And when we do that, we get E of R times 4 pi R squared is equal to Q over epsilon naught, and that tells us that E of R is just our classic Coulomb's law, Q over 4 pi epsilon naught R squared. And that means we can do another piecewise function for the electric field. It is Q over 4 pi epsilon naught R cubed. Remember, that's just a constant, that R, that uppercase R there, times R hat for R less than big R, and it's equal to Q over 4 pi epsilon naught R squared R hat for R greater than big R. Now, if you actually plug in R equals big R, what you'll see is that the two formulas give exactly the same result. Do you see that? If I plug in R, little r equals big R, I end up getting the exact same result for both of them. So we can add an equal to symbol on there, and I put it in red so you'd notice that we did it. So this is our electric field that we found for a non-conducting sphere of radius big R, total charge Q, distributed uniformly throughout the non-conductor. Now, if I go to graph this one like I did last time, we'll see a bit different graph than we had before. And this is R, and this is E, and this will be Q over 4 pi epsilon naught R squared. This will be R. And now I'm going to take and say that this is the dot that we have. But for R less than R, it's just a linear graph, so it'll be just it'll just be a straight line. And then for R greater than R, it falls off like 1 over R squared, so it's identical to the last one for that area. I did write squared on that one. Yeah, I did. So that's how the electric field behaves for this non-conducting sphere. One thing we did skip, remember I told you didn't have to do calculus to do the right-hand side of part A. What I could have done there, just to let you know, is I could have said, I'm going to write this in green so it'll show up as something different. Oops. I wanted to underline that in green to know that's where I'm coming from. So the integral of rho dv would equal, we've already figured out what rho is. It's Q over 4 pi, or excuse me, over 4 thirds pi r cubed. and then we got times the integral of dv. And the integral of dv should just be 4/3 power cubed. But what I want to do is show you that the dv we'd want to use there is 4 pi r squared dr. In other words, we imagine the inner surface of a spherical surface has a radius of little r, and then we imagine that it's thicker than that by an amount dr. So, in some sense, if we take the surface area and multiply it by dr, it gives us an area. When technically we'd have to do the volume of a small sphere subtracted from the volume of a big sphere. The small sphere would have a radius little r. The big sphere would have a radius parenthesis r plus dr close parenthesis. So if you actually did that subtraction that way, it would come out with this same formula that I used, 4 pi r squared dr, but there'd be other terms that might have a dr squared in it or a dr cubed or something like that. And since, the nature of a integral is that we try smaller and smaller drs until it gets basically infinitesimally small. So clearly if you're dealing with a dr, the dr squared is nothing. Because if dr is really like a 1/1000th, then dr squared would be 1/1 millionth, which is literally 1,000 times smaller. Okay. So when you did this, what you'd end up getting is q over 4 pi r cubed times 4 pi integral r squared dr. And that, of course, is 1/3 r cubed because we're integrating from 0 to big R. And you can see now that, in fact, the 4, the pi, the 1/3, all of that cancels out with the R. And in this case, actually, I'm supposed to do it to little r. Excuse me. So integrating that to little r, you can see that I would ultimately get 1/3 is supposed to be little r cubed. So this whole integral here is going to become 1/3 r cubed. So you can see that the 4 cancels out with the 4. The pi cancels out with the pi. The 1/3 cancels out with the 1/3 that was down here, but evidently I forgot to write it. I just said it. So now I'm going to say cancels out with this 1/3. And we ultimately just get q r cubed over big R cubed, which is exactly what we got here. Okay. So that's how you'd actually do the calculus part, which you don't want to do. Okay. But the next one we're going to have to do it anyway, so it's no big deal. Any questions on that one, Jen? All right. So we have another example. It's another non-conducting solid sphere. So a non-conducting solid sphere of radius big R has a charge distribution of rho equals a constant times r squared, where c is the constant. If the total charge is capital Q, A, determine C and its units, and B, determine the electric field everywhere. So I'm trying to show you, how you can soup up these problems, look a little different from the simple ones that we have as examples in our book. And this is one of the ways you can actually use a charge distribution that's a function of R, or a function of theta, or a function of phi. In almost all cases, you can't do any of those, but you can do ones that are like R squared or X squared. And sometimes you can pull off a 1 over X squared or a 1 over X or a 1 over R or 1 over R squared, but that's about it. So let's do this one. We'll say solution. So what we know is that Q is equal to the integral of rho dv. That's one thing we're going to find out. We want to know what C is equal to, and we want to know what the units of C is equal to. And then we want to know what the electric field is everywhere. So that's what we're shooting for here. It is non-conducting, so the charges are going to stay fixed wherever they are. I'm going to start off with part A, and I'm going to say Q is equal to the integral rho dv, and we're going to have a spherical distribution of charge again. So let me draw my coordinate system. Okay, so this will be my x-axis, y-axis, z-axis. Uh, I'm going to draw my sphere purple this time, and I'm going to make it 3 blocks in radius. And I'm going to try to draw it from down here because it looks like when I draw it from down here, I'm able to do it a little better. Oops, scratch that. I put my hand off of it. So there we go. We've got our sphere of radius big R, our sphere of radius big R, and our sphere of radius big R, like that. And I indicate as much by writing a big R right here and a total charge Q. Now, what I'm imagining here for this integral portion, I'm going to draw a little spherical shell inside. And that did not go as planned. Let's try it again. So there's part of the spherical shell. This is the inside part, which has a radius of r. Now the outside part is going to have a radius of r plus dr, and therefore it's going to look like this. It got a little off whackety whack, but I can try to fix it a little bit. Okay, that's cool. So that's the spherical shell we were talking about, and therefore the volume element is going to be 4 pi r squared dr. So I'm going to say this is equal to the integral of that c that we talked about times r squared times 4 pi r squared dr, and I'm going to integrate from r equals 0 to big R. So I know I can pull the 4 pi and the c out in front. That's going to be 4 pi c times the integral. Now I have r to the fourth left, dr from r equals 0 to big R. That's going to give 1/5 r to the fifth. So our answer is 4/5 pi c r to the fifth. Now, since that's equal to Q, we say Q is equal to 4/5 pi c r to the fifth, which means C, which is what we're looking for, is actually equal to 5Q over 4 pi r to the fifth. So from that, you can see also that the units of C must be, any idea on that one, Jen? What the units would C of C would be?
No, it's the R's, are they supposed to be little R's? The R to the
Uh,
fifth?
Not in this case, because I'm actually doing, I was doing the whole integral over the whole
Okay,
surface so that
yeah.
I could find out what Q was, or C was.
Okay, so then that R to the fourth should be a big R.
Yeah, yeah.
That's a little R.
Oh,
That's
yeah,
what
I
I was
drew it up there. Yeah,
confused about.
gotcha. Yeah. Oh, okay. So yeah, the r to the fourth was actually a little r because that was the variable we're integrating with respect to. But
Uh-huh.
the biggest of the values of little r is big R.
Bigger,
So
okay.
that's why it was little r in the integral and it came out as big R in the at
Bigger,
the end.
okay. I
Okay.
lost track of it.
No problem. Well, the pi
Okay.
has no units and the 4 and the 5 have no units. Do you remember what the units of Q would be? Q is charge, person's name.
Coulombs per
Yep.
meter? No,
Yeah,
you
close.
told me earlier. I wrote it down. I can't remember.
You said coulombs per meter. That was close.
Okay.
Coulombs per meter would have been lambda. Uh, but we're actually solving for a constant in it. But you look at the formula, do you see that you have a Q and you have a R to the fifth? So the actual unit should be coulombs per meter to the fifth.
Oh, meters to the fifth. Okay.
Okay, that was the big thing here. I just wanted to make sure y'all realized how we were doing that. So it's coulombs per meter to the fifth power. And now we have both of our values of C and our value of uh, the units of C. Okay, so we got part A done already. Now what we're going to do is work out the electric field. So let's go ahead and make our hypothesis. So this is part B. Our hypothesis, since the rho was radially symmetric, was dependent on r, we know that it's still going to behave like a sphere. If it was like dependent on some angle theta or some angle, a polar angle like phi or something, the spherical symmetry might not be as not be the result, so we wouldn't be able to do that. But in this case, I made it proportional to r squared, so our hypothesis should be that E, the electric field, should be some magnitude that probably only depends on r, and it should point radially outward again with the spherical r hat vector. So that's my hypothesis. And I guess since you've had enough experience with these three spheres that we've done already, you should know that what the dA is going to be and all that good stuff. So I'm going to write down left-hand side of Gauss's law, and that is the closed integral of E dot dA. And now I'm going to substitute in the values. That's going to be E of R hat dotted with dA R hat, which is just going to be E of R times 4 pi R squared. So remember, that's actually completely sufficient for the spheres. You don't need any more steps than that. I showed those other steps to you so you'd understand what's going on, but you can go straight from that first expression next to the left-hand side to that second expression and then the third expression, and you're done. You don't have to, show all those gory details. Now I'm going to do the right hand side, and we're talking about for r less than big R. So our Gaussian surface is actually a sphere inside again, but the right hand side is Q enclosed over epsilon naught. There are nice, neat little ways where you can avoid doing the integrals again, but I'm not even going to try this time. I'm going to do it this way. I'm going to say this is equal to 1 over epsilon naught times the integral of rho dv. Only this time I'm integrating from r equals 0 to little r because my Gaussian surface is a circle of radius little r. I didn't draw it this time, but let me write it here. Is a sphere of r. In other words, it's just a sphere of radius r, which is less than big R. So now that's why I'm integrating out to r. And we already know that the row was c times r squared. So I'm going to pull the c out in front with the epsilon 0. And now I'm going to go r squared. And then my dv is going to be 4 pi r squared dr. So I'm going to get 4 pi c over epsilon naught times the integral from 0 to r of r to the fourth dr. So we're going to get that is 4 pi. Ooh, all of a sudden it just started trying to draw the perfect shapes again. I don't know why it switches that on its own, but anyways, 4 pi c over 5 epsilon naught r to the fifth. Now I've got to plug in my knowledge of c. So I'm going to say 4 pi over 5 epsilon naught. And then my c, remember we found that was 5q over 4 pi r to the fifth. And then all this is times r to the fifth as well. So we could now see that I'll use green for the crossouts. The 4 pi cancels out with the 4 pi. The 5 cancels out with the 5. And lo and behold, we get just q over epsilon naught times r to the fifth over r to the fifth. So that is the right-hand side. Notice it came out a little nastier than we expected. But, we did have to do some calculus. I'll show you in a second how you could have avoided doing calculus on that one. But I think in this case, it's probably a little more straightforward to do the calculus way. Now that I have the left-hand side and the right-hand side, I can say left-hand side equals right-hand side. And what we get is E of r times 4 pi r squared. As always, it's an electric field times an area is equal to q over epsilon naught r to the fifth over big R to the fifth, which is just a constant, don't forget. But now what you can see is the r to the fifth is going to cancel out the r squared and just leave a cube over here. So at least for the r less than big R case, we're going to have the electric field E is actually equal to q r cubed over 4 pi epsilon naught r to the fifth times r hat for r less than big R. So now we have the electric field inside. Not too bad, right? Now I got to do, now we calculate E for R greater than big R, which means so we now have a Gaussian surface that is a sphere of radius little r that happens to be bigger than big R, even though I'm not showing it on here. So now I'm going to do the same hypothesis and all that stuff. So we get left-hand side, closed integral E dot dA is equal to the integral E of r hat dot dA r hat, which equals E of r times 4 pi r squared. We have right-hand side. which is Q enclosed over epsilon naught. And of course, we're at a Gaussian surface that's bigger than R, so all the total charge is enclosed, so it's just Q over epsilon naught. So we finally have left-hand side equals right-hand side. Boy, my S's are getting worse and worse. They're looking more and more like horrible integrals. Anyways, E of R times 4 pi R squared equals Q over epsilon naught. So E, the electric field, there it goes, switching to, dang it. There you go. There it goes, switching to the automatic pretty drawing for some reason. So I'm going to say the electric field E is equal to, piecewise again, Q R cubed over 4 pi epsilon naught R to the fifth R hat for R less than big R, and it's Q over 4 pi epsilon naught R, R squared R hat for R greater than big R. And if you actually plug in the R's, the big R for the little r, you'll see again that they're actually equal at, they're equal at R equal big R. So I can add that little greater than or equal to symbol. And we now have the answer for the electric field in all space. Any questions on that one? All right. Well, the way we could have done that other part without using integrals, we could have just realized that the charge density, though it's not a constant, it definitely has a very specific value. So we could use something like, rho inside equals rho outside. And if I did that, it'd be something like Q, or excuse me, it'd be something like what do we have? We had C times R, or excuse me, C times R squared is equal to C. No, that doesn't work either. Actually, I'll show you that later. I'll get a cleaner idea of how to do it. I think all I wanted to do now, in addition to this, these major ones, was let me check my notes, see if I did last time, if I did an infinite plane. I did not. All I did last time was a sphere and a cylinder, which gave us the result we got before. So I'm going to go ahead and do the infinite plane and, oops, wrong thing. Yeah, I'm going to do the infinite plane, and here's how that works. I'm going to start off by, and this is example 4, I'm going to start off by drawing the diagram. So my coordinate system is going to look something like this. Okay. And I'm going to say my infinite plane is going to be this, 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 this. And that means it goes on for infinity that way, and this way, and that way. And of course, all the other ways as well. This is going to be my x-axis, this is going to be my y-axis, this is going to be my z-axis, and I'm going to say that it's uniformly distributed charge. Sigma is equal to a constant. So find E everywhere. Oops. With a uniformly charged sigma equals constant, infinite plane. Okay. Solution. So we're using the closed integral E dot dA equals Q enclosed over epsilon naught. We're also using sigma is equal to dq over dA. And I'm going to choose a very specific Gaussian surface. In fact, the Gaussian surface is going to be what we call a Gaussian pillbox. So it really is just almost like a thermos or a soup can. I often refer to it as a soup can. And it's going to penetrate through the plane and be on the underside too, like that. And up here on top, we're going to have a little differential area element, dA top is equal to dA top k hat. We're going to have a similarly drawn one down here, only it's going to point down. So that's dA bottom is equal to dA bottom times negative k hat. That's because it points down. It has to be negative k hat. And then the sides have that little patchwork there. And this is what I call dA soup label is equal to dA soup label times, let's call it rho hat. Last time I did R hat, but then I put like CYL next to it because it was the cylindrical R hat. So I'm just going to use rho from now on just to make that easier. So rho hat equals cylindrical coordinates, or polar coordinates is another way of looking at it, because remember you did do polar coordinates probably in trig. So cylindrical polar coordinates, which are equal to cosine theta I hat plus sine theta j hat. Not that you need to know it, but just to refresh your mind that it has no k in it. Hypothesis, that's what happens when I waste time by trying to save time. The hypothesis is that E is equal to some positive E of Z k hat for Z greater than 0, and it's going to be some minus E of Z k hat for Z less than 0. So that's my hypothesis, and you'll see now that the soup label and all that stuff, I basically had it exactly reversed because I didn't take the time to do the hypothesis part. So the left-hand side is going to be the closed integral E dot dA, but I have three different surfaces. I have the top surface, the bottom surface, and the soup label. So I got to do all those. First, the integral over the soup label. This is why I had to put plus or minus E of Z k hat dotted with the dA for the soup label is dA soup label rho hat. Yes, that's right. Now I'll say plus the integral over the top is going to be positive E of Z k hat dotted with dA top k hat plus the integral over the bottom of negative E of Z k hat dotted with negative dA k hat, but that's dA bottom. Okay. So this one, the first integral can be integral plus or minus e of z. Notice the z actually varies. I can't call that constant, so I can't pull that out in front of the integral. I can still, because the dot product is linear operator, I can still pull the SL through the dot product, but now I'm left with k hat dot rho hat, which is, as I've shown you a few seconds ago, 1 times cosine 90 degrees, which is 0. And then we get plus. On this case, we just get e of z integral dA top k hat dot k hat plus e of z. Notice you had a minus and a minus gave us positive. So integral dA bottom k hat dot k hat. Those two are equal to 1. So the left-hand side just becomes 2 times e of z. And that's it. Okay, so again, we got a, or 2 times a, I should say, where a is going to be the top surface. So as I was getting ready to say, and this is why I caught myself, it's always going to be electric field strength times some area or maybe a number. In this case, I got 2 E of Z times A, and A is just supposed to be the area of the top or bottom. And I said slash there because they're both the same. Okay. Now that I got the left-hand side, I can do the right-hand side. Sorry about it taking so long. The right-hand side is Q enclosed over epsilon naught. We did find that the charge density is sigma. So if you take sigma and multiply it by an area, you'll get a charge. Well, the area of the top, since this is a cylinder, is the same as the area where the cylinder runs into the flat plane. So that's an A as well. And then it's an A again at the bottom. But what matters here is the area of the actual plane that's enclosed is also an area A. So this right-hand side becomes sigma A over epsilon naught. Now I'm going to say left-hand side equals right-hand side. And from that, I get 2E of Z A is equal to sigma A over epsilon naught. And you can see the A's cancel out. And lo and behold, we get the electric field E is equal to, from our original hypothesis, it's going to be sigma over 2 epsilon naught k hat for Z greater than 0, and it's going to be negative sigma over 2 epsilon naught k hat for Z less than 0. And again, you can see the discontinuity here. There is a discontinuity, and that discontinuity is exactly sigma over epsilon naught in this case. So that fits what we said earlier about the discontinuity in electric field component perpendicular to a surface. It's only discontinuous if there's a surface charge, and if it is, the discontinuity would be the surface charge divided by epsilon naught. And you'd see it's sigma over 2 epsilon naught above, and then sigma over 2 epsilon naught negative below. So if you did sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught, you get sigma over epsilon naught. So that the electric field really just looks like this. Z is here, E is here. This is going to be sigma over 2 epsilon naught, and the electric field is going to be this. And then if I go down here and say this would be negative sigma over 2 epsilon naught. And what we can see is the discontinuity sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught equals sigma over epsilon naught, and that's a check. And that's it. Okay. Make sure you look at the example where they talk about a cavity inside with a charge inside of it. That was the only other thing I was going to do, but we definitely ran out of time. Thanks for sticking around with me, Jen. I appreciate you doing that. You didn't have to, but I do appreciate it. And you're free to go, but you're also free to sit around and ask me any questions you might have.
No, but can I still come for the face-to-face test on Monday?
Yes, yes, you can. No problem.
Yeah,
Do you know what
I don't
time
think
you
you're gonna
plan
be
on
closed.
coming?
Probably the 9 or 10 one.
Okay, no problem. My class
Is
starts
it,
right
you
at
said
9.
every hour, right?
Yeah, yeah. My class starts right at 9. Giving me a break up until 10, that really works pretty well. So if you can do that, that'd be great.
Wait till 10. Okay, yeah,
Yeah.
sure.
Do you have a laptop or anything you'd use on your own, or you want to use one of our computers?
Either or.
Okay, that's cool. If you have one that can use the Wi-Fi, can log into Canvas, and can run a lockdown browser, then bring it. If not, it's okay. We have one that you can use. Okay.
Okay.
Don't forget, you do
What
have that
what
test.
room?
I'll be JC. This is Monday, so it'll be JC 26. Yes, JC 26.
Okay, cool.
Okay.
10
Thanks, Jen.
a.m. Great. Thank you.
Have a good one.
You too.
Bye.
Bye.
All right, so we got that. Bar one almost careless mistake with computing the left-hand side of that, but luckily it looks like we've figured it out. We got discontinuity we expected. I just didn't get to cover the cavity inside of a body, but that just shows us basically because the electric field inside of a conductor is zero, it makes the inside of the cavity have the opposite charge of anything that's inside the cavity. So if you had a charge of plus Q inside the cavity, the inside edges of the cavity would have a charge of minus Q. That way, the total charge inside a Gaussian surface that encompasses the cavity but is in the actual conductor, that has to give you electric field equals zero, and that can only be zero if Q enclosed total is zero. And that's why we reached the conclusion that if you have a charge of plus Q inside of a cavity, the inside surface of the cavity will have a charge of minus Q. If you had a minus Q inside the cavity, the charge on the inside edge of the cavity would be a positive Q. And then if you had a total charge Q on the conductor to begin with the cavity in it, and then you put the charge little q inside, then you'd have a little positive Q as the charge inside the cavity, a charge of little negative Q on the inside edge of the cavity, and then a charge of Q plus little q on the outside of the whole solid conductor. So check that out. Make sure you ask me questions if you have any. And that's it. You're free to go. See you, everybody.